Okay, so let's have a look. So basically the question could be so many different types, but what it really matters is the understanding and the thinking goes behind it, right? And that determines so this is something what we call a force analysis, okay? So what is force analysis means I'm looking at the forces acting and I'm figuring out, well, how do these forces work together, okay? All right, so say let's have a look at this situation over here. It tells me the box is sitting here stationary. It gives me an angle, it gives me a mass. There's nothing else. And I need to think, okay, what are the forces acting and how are these forces going to interact with each other? But the cue it gives us is it gives us this concept called stationary. So now, first thing we need to know, if it's stationary, what does that tell you about the forces? Balanced, yeah. So the key thing is the forces are balanced if they're stationary, right? Okay, and then the second thing is, it doesn't tell me what are the forces acting, but we need to think, okay, so what could possibly be the forces acting, right? Well, first one, what is one force? It must always be acting. Gravity, right? So we start with gravity, because gravity always exists, you can't take gravity away. Other forces cannot exist, but gravity must exist. Okay, so when I draw it over here, let me draw gravity, I draw it start from the middle, and gravity always goes downwards. That's the first force you will have. Does it make sense? Well, previously we have like a dropping of a situation. If it's dropping, gravity is only a force, there's no other force. But this situation now, we got an issue here. The issue is I have a block over here. This thing is gonna be supporting it, right? So if there's something in the way, now what kind of force does it give the box? That's the support force, or we call it the reaction force, right? Okay, so something special about reaction force. Reaction force is, if I give it 100 Newton pushing down, it's gonna give me 100 Newton going up. If I push it 200 Newton, how much force does it give me? 200 Newton. So that's something about reaction force. Reaction force can be as big as the thing is pushing the box, right? Okay, so I'm gonna draw the direction of reaction force. I'm gonna draw it. The direction goes in this direction. Because reaction force is always 90 degrees to the surface. That is what's so special about reaction force. Do I have this in the notes? Oh, no, okay, sweet. So I'll write a little bit notes over here. You can add this into your book later, okay? Because I think I probably give this to my, anyway, don't worry about it, okay? I'll just say here, reaction force is always perpendicular to the surface. And then the reaction force, I can also call it the support force. I'll give it a little stop, and that's important to know. Say the reaction force I have right now, what is the direction it goes? It goes upwards because my feet, because I'm standing on this surface, the surface is horizontal, so it must be 90 degrees, okay? Say this, if I'm just lying here supporting on the wall, so now what is the direction of the reaction force now? Yeah, now it's going to come this way because that's where the surface is pushing. Surface is going this way, so the support force will start to go this way. Okay? All right, so in this case, it will be 90 degrees to the surface, so it goes that way. Okay? All right, and the next thing we have to figure out is there going to be any friction? If there's no friction, if it's slippery, the thing is going to start to slide downwards, right? So we have to think, well, is there actually a force pulling it downwards? Is there a force over here trying to pull it downwards? There's nothing there, right? If there's something there, I have to ask you, well, what is that thing? There's nothing there pushing it. So that's it. These are the two only forces that has to be there. And another force, it could be there, is the friction force. Okay, so now I'll say, what's so special about friction force? Friction force is always parallel to the surface. Acting against relative motion. Okay, so this is parallel to the surface. The relative motion is it wants to go down, and friction trying to stop it and make it going up, right? Okay, so I just add one more thing over here. So the other thing is we commonly see is called tension force. I think we teach this at year 11 as well. Tension force is always comes in pairs. They are equal in size. Goes both ways along the string. Put a little star over here as well, because this is something we always use as well. And tension force exists in like anything that's stretchy or something. Say if I give Hannah this clothes, pull it. If Hannah is pulling it that way, there's a tension force going this way against her. If I'm pulling it this way, and there's tension force inside there. So what direction does tension force go depending on who you're analyzing? If you're analyzing me, the tension force goes that way. If you're analyzing her, the tension force going this way. Does it make sense? Okay, sweet, thanks. Okay. And the force always equal to size. It doesn't matter who has a bigger force, even if I'm moving her along the way, but the force is action force, reaction force. According to Newton's third law, action force always equal to reaction force. Same as this thing. If you push down, same force pushing up. Okay, all right. And now that's it. That is forces acting over here. And then the next thing is, well, how does these three forces gonna cancel each other, right? We talk about these forces are gonna cancel each other. So the first thing I can do is I can calculate the gravity force, which will use mg. It's going to equal to 98 Newton. That's the first step I can do. Most easy. I found the ones I know. Okay, and then this is the skill you need to have with vector components. These two are 90 degrees to each other, right? And this one is diagonal. It's not in the direction. So typically, if we have a side, we make it horizontal and vertical. But this one, we actually need to decompose it. One going this way, and then one going in this direction. Does this make sense? Okay, so when I draw it, when we decompose forces, we always need to make it to become a rectangle. So 90 degree is all 90 degree over there. There will be a 90 degree over here as well. And now you can see, well, why does the object want to slide down? The object wants to slide down because the gravity force going down can have a component making it slide down. And this component wants to make it to go downwards. Does it make sense? And then there is another component pushing against the thing. So however much it's pushing against, 100 Newton, they will give you 100 Newton. If you're pushing 200 Newton, it will give you 200 Newton. So the reaction force will always equal to this component. Does this make sense? Okay, so I'll write over here. Say the reaction force will always equal to the gravity component that's pushing against the slope. I'll say the perpendicular to the surface component. Yeah.
Does that have a name?
It's just the component that's perpendicular to the surface. Yeah.
So it's not a force?
It is a force. It's a component of the force, which is a force.
Okay.
Yeah. And the language over here is a bit confusing, right? So sometimes you can just make it easy. You can just call this F1 and this is F2. You know it's a F1 component of gravity, F2 component of gravity. Or sometimes you can say, well, this is my F gravity, say dash. This is my F gravity dash 2. It doesn't matter what you call it. But you need to know this is the perpendicular. And then that is the parallel component, okay? So let me call this FG1, and let me call this FG2. Just easy for me to analyze, because, but in terms of explaining question, you have to use these words, okay? All right, let's say this. Then the gravity, there's another force, say gravity has a component. Oh, I'll say here, I'll say this, let's say friction. And friction force is interesting as well. Say, if I'm pushing 20 Newton over here, that way, how big is the friction? If I'm pushing 20 Newton, I'm pushing this way, 20 Newton pushing forward, how big is the friction going backwards? 20 Newton going backward. If I push 100, how much friction going backwards? Still 100, and the table is not moving, right? But friction has a maximum value. If I push so hard, say I'm pushing 10 Newton, not moving, 20 Newton, not moving, and then bang 30 Newton, it started moving along, right? So that's because friction has a maximum value. Does this make sense? Yeah, and once you pass that maximum value, then friction don't equal to that force anymore. So say if this friction, the maximum value is 20 Newton, but you got a 30 Newton over here, so it will start to slide downwards. Okay, yeah, but for the moment over here, because I know it's stationary, the friction force must equal to that force going downwards, right? Okay, so I'll say over here the friction will equal to the gravity component. Again, it's not gravity, and it's not another force, it's the gravity component. That's going down the slope. And I say, how did I know that? Because the object is stationary. So forces must be balanced. Okay, so these things are very important because explaining questions, this is how you answer them, right? Okay, and then the next step is I'm going to do my calculations now. The calculations, I mean, gravity is easy to calculate. And then the next thing you need to calculate is I need to know the angle. But the angle they give you is this 30-degree angle. And it's important for you to figure out because we're trying to do this little rectangle over there, right? Okay, after you all write down the notes. Okay, if you do this question like so many questions, and then it becomes really easy. The small angle will equal to the 30-degree. Okay, so this angle will equal to 30-degree. Okay, that's the rule. If you remember that, then easy. Okay, but let's say you don't know that. So how do you know this angle is going to be 30-degree over here? You go like this. Well, this is 30-degree. I'm going to ask you how big is this angle over here. That's then going straight down. So there's a 90-degree over here. There's a 90-degree over here. That must be a 60-degree because 30 at 60 at 90 become 180, right? So this angle must be a 60-degree. If this angle is 60-degree, how big is this angle? You can see these things are parallel. If this is 60, that will be 60, right? And this is parallel and this is perpendicular. There's a 90-degree over here. If there's a 90-degree here, that's 60. That must be 30. Does that make sense? So if they give you the angle 30, 20, or 10, it's very easy for you to tell because you just look at it. If it's small, then that's 30. If it's big, then it must be 60 because it could either be 30 or 60. Does it make sense? So, but if you had the situation where that angle is 40-degree, and then it's very hard to tell if it's 40-degree or 50-degree because 40-degree and 50-degree are very similar to each other. Does that make sense? So then you will need to go, yeah, that's 30, that's that. But for the most part, you can just say, well, that small angle must be 30, and then the big angle must be 60. Okay. All right. So now I just need to use trigonometry to calculate now. So for this part, I mean, take your time. If you're very good at trigonometry, you just go straight away into it. If you feel a bit slow, I'm going to use SOHCAHTOA, and you go use SOHCAHTOA. Okay. So take your time, and then say, for me, what I'll do is I'll do here. So now, according to these two rules, I've learned the reaction force has to equal to my Fg1. Okay? And then I go, well, how big is Fg1? This is 30, so you use cosine. So it's cosine 30-degree and times your gravity force. Okay? And then you put that in your calculator, so that becomes cosine 30-degree times the 98. You'll get the value. And then this one over here, this value equals to this value over here. Because rectangle, two sides are the same size. So now you have a sine 30-degree. Okay? Or the other option is you can say, well, if that's 30-degree, this is going to be 30-degree. Right? If that's 30-degree and that is the sine value you have over there. So now if friction will have to equal to the gravity component 2, that equals to a sine 30-degree and times the gravity force. So that equals to sine 30-degree times 98. That will give you 49 Newton. Does that make sense? Yeah. Okay. Can someone quickly calculate this value for me? Sine 30 times 98. 49? Oh, that's sine.
Wait, sorry.
Yeah. 84?
Now it's 85.
85. Okay, so let's say this is 85 Newton. Yeah, so I run it to whatever significant figure I was using because my value cannot be more accurate than the original value. The original value was 9.8 I was using, right? So I keep it to 2 significant figure. Okay, yeah, that's it. And then bang, I solved this problem. Okay, and again, so the skill behind it is the most important thing because the question could change. They could give you bang another situation, right? So let me just give you a random situation. Okay, are you guys happy with this? Okay, let me take this away, over here away. Let me give you a random situation. I want you guys to have a think, well, how are the forces acting? I mean, we have the situation where you're pulling a rope, right? Pulling the rope in the box. But let's say we have this situation. Let's say we have this situation over here. Can you guys have a think? What are the forces going to be acting? What is the first force?
Gravity.
Yeah, always gravity. Gravity is always the first force going down, right? But the box is not dropping down. There must be forces holding it, right? And there are 2 strings holding it. So what is the direction of tension force? So one tension force must be going in this direction, Ft1. And then there is another tension force inside this string going in this direction, Ft2. Does it make sense? Okay, and then have a think, how does these 3 forces going to be balanced over here? Yeah.
Ft1 plus Ft2 has to equal to force.
Yeah, this one and this one have to equal to this one, right? But these are not in the same direction. If they're not in the same direction, I must make it to become the components so they can be in the same direction. Does it make sense? Just like this one. Well, this one and this one, they're not in the same direction. So what do? I have to make this one to become in the same direction as them to cancel it, right? So this one, what you can do is this. I can make this one horizontal. So it will have a vertical component going up, right? And then I can do the same thing with this one. This one will have a horizontal component, and it will have another vertical component going upwards, right? And now it becomes a lot easier. Say this, why does this thing not dropping? It's not dropping down by gravity because there are 2 components over here going upward. And these 2 components add together is going to cancel the gravity. Does that make sense? And this force have a gravity component, have a force component to drag it to the right. If you think about it, if it's drawing you this one, it's going to make the thing move right? But it's not moving to the right because this one have a component going to the left. So now the right is going to cancel the left. So these 2 forces must equal to each other. And then together now, we've canceled all these 3 forces to make it become 0. Does that make sense?
So what does the box do? Is it just
stationary? Yeah, the box is hanging over here by 2 things supporting it. Does that make sense? Okay, so this is what we call force analysis based on what we know about tension force, gravity force, support force, reaction force, and then we go to try to analyze the situation. Okay. All right, so we're gonna stop it over here.